All right, so this is, believe it or not, take 4. Me trying to get example 2 to you guys with both sound and image. For some reason, the WebEx, I still haven't figured that out, did not record my screen, even though it was recording the WebEx session supposedly. In any case, I'm now trying to sort of redo this, hopefully somewhat quickly, so you guys can at least have some description and all of the images and the notes at the same time. So if I sound a little bored, I apologize for that, but this is, again, like my 4th time going through these 4 slides. So so the issue here, what we're trying to do is solve for the displacements, flexural deformations or flexural displacements of a simply supported beam with a point load in the middle of it. And the reason this is more challenging than the previous example, example 1, which was a simply supported beam with a uniformly distributed load, is that the point load here is a discontinuity. And so what it means is I cannot define a single moment diagram for this structure that will be valid between point A and point C. I can define one moment diagram that will be valid between A and B, and then I can define a second moment diagram that will be valid from B to C, right? But nothing will be valid from A to C. So we're going to need 2 moment diagrams, one for each part of the beam. And then when we integrate those twice, each one is going to have 2 constants of integration. So we're going to have a total of 4 constants of integration, and therefore we need 4 boundary conditions to solve for those 4 constants and ultimately for the elastic curve, right? So the process here is very similar to what we have done in the past in terms of drawing moment diagrams. Because we've got this discontinuity in the middle, we have two segments, and we have to make a cut through each one. So you can see the first segment here. The first segment here, how come that's not drawing? There we go. Is segment 1. So I'm going to make that cut, and that is here, solving for the moment diagram of that segment, right? So the reaction is P over 2, and the dimension from that reaction to where I'm making the cut is x1, and so when I solve for that, I get this guy right there, right? That my moment is P over 2 times x1. Importantly, that is valid only from 0 to L over 2. Again, I cannot say this enough. There is no moment diagram that is going to be valid from A to C. And I know some of you are still going to try to define one, but I'm telling you right now, do not do it. Right? If I have to say this 1,000 times and I can stop one person from trying to do it on an exam, it's worth it for me, because it's frustrating to say this so many times and then still have people make that same exact mistake. But because there's a discontinuity, we have 2 moment diagrams, right? So the first one is here. The second one is here. So we're taking a cut now between the point load P and the right-hand support, right? Now, one thing you'll notice here is I have retained my coordinate x1. So I'm still going to use x1. Now, when we did actual calculations of moment diagrams, we would have actually defined a new coordinate system that came from the right-hand support to the cut, right? I would have defined a coordinate system that looked something like that, right? But we're not going to do that now. And the reason we're not going to do that is if I define a coordinate system that goes from right to left, my rotational sign convention gets flipped, right? So if you look on the left-hand side here, I've got a positive x, a positive y, and I'm showing you the positive z. To get the positive z, you've got to curl your fingers from x to y, right? And so that is a counterclockwise or positive right-hand rule out of the board, right? Now, if I take that x coordinate and I flip it over so it goes from right to left, now when I move my fingers from x to y, that z coordinate is into the board, right? And I do not want to have two positive rotation sign conventions for the same problem. So I know that might have sounded a little confusing. If it did, all you got to remember is this guy right here. I'm going to circle it again. Right? For these problems, you make sure all coordinate systems go from left to right. Period, full stop. Right? Do not try to define one from right to left. You will confuse yourself. Right? Is it possible? Sure. You just have to then go through and multiply all rotations of one of those elastic curves by a negative sign, right? But we're not going to do that. We're just going to define them so they all go positive from left to right. And if you do that, you see here, this is your moment diagram, PL over 2 minus PX1 over 2, and that is valid from L over 2 to L. Right, so again, two moment diagrams because we have this continuity, discontinuity in the center that's caused by the point load. Okay, so now if I go back one, right, so I can erase this guy, I will draw what that moment diagram looks like. It looks just like this, right? And the peak moment there is PL over 4. So if I plug in L over 2 for x1 here, I get PL over 4. If I plug in L over 2 for x1 here, I also get PL over 4. Right? That's important because it doesn't matter, one of these expressions is the, sort of the ramp going up, and the other one is the ramp coming down. But at L over 2, right, the moment has to be PL over 4 on both of them. Otherwise, there's a jump in the moment diagram. There is no concentrated moment applied there. So that can't be right. Okay, so now if you look what I've done on this beam, the left half of the beam is gray, the right half of the beam is green, right? They're the same beam, just two different segments of them. So the gray is segment AB, and the green is segment BC. So I'm trying everything I can do to avoid anybody trying to treat this as a single segment, right? Point load, discontinuity, you guys are sick of hearing me say it, but hopefully nobody makes that mistake on the final. So here we go. So everything that's in gray is segment AB, right? So what I've done is I have taken the moment diagram for that, which is right there, Px1 over 2. I've divided it by EI, that turns it into the curvature diagram, and then I can integrate it twice, right? Every time you integrate it, you get a new constant of integration, right? And so you see what's boxed in gray there? That is the elastic curve for segment AB, right? And it's valid again from 0 to L over 2. That's how segment AB is defined, right? And then if we try to go to the green segment, now that's segment BC, so I'm going to try to write everything in green. The moment diagram is now this, PL over 2 minus PX1 over 2. So I divide that by EI, turns it into its curvature diagram, and then I just integrate that twice, right? So I end up with this elastic curve that's shown in the green box, right? So that is valid from L over 2 to L because that is how we define segment BC, right? It begins at L over 2 and it ends at L, right? So I now have these 4 constants of integration and I need 4 boundary conditions to solve for them. So the ones that we have, and if you look here on the lower part of the slide, I'm redrawing my simply supported beam with the point load in the middle, and then I'm drawing the deformed shape. And what you notice for the deformed shape of the gray segment, segment AB, and the green segment, segment BC, is that they have the same displacement and the same slope under the point load, right? And they have to, because compatibility ensures that there are no unintended breaks or overlaps, right? So that's the black text on the right. And so those two compatibility conditions, right, are actually boundary conditions for segments AB and BC, because they're at the boundary of AB and the boundary of BC, right? They are defined in relative terms. So I'm not telling you what the displacement is under the point load, right? That's what actually I'm trying to solve for. I'm just telling you that the displacement of the left-hand elastic curve, the gray elastic curve, and the displacement of the green elastic curve are exactly the same at x equals L over 2. Right? I'm also telling you that the slope of those elastic curves have to be the same at x equals L over 2. Right? And then, of course, you have the boundary conditions at the beginning and the end of the beam. So at x equals 0, I have the displacement is 0, and at x equals L, I also have the displacement is 0. Right? So those are points A and C. Right? Okay, so those are our four boundary conditions. And then if we move to solve for them, right? I'm not going to go through the math here, but you have four equations, and you have four unknowns, right? So you can solve, right? So the equations are these boundary conditions, right? You just plug in the v of x1 and v of x2, the greens and the grays, where they go. And then you can solve for your four constants, C1 through C4, and you should get these four constants, right? And when you plug in, you will get the elastic curve for segment AB, right? You see it there. That's valid again from 0 to L over 2. So that's segment AB, the gray one. And then you also get an elastic curve for segment BC, which is the green one, right? And that one has a bunch more terms, right? And that is valid from L over 2 to L, right? And if you then plug in v of L over 2, you get that you get minus PL cubed over 40 ADI. Right? So that's sort of where we are here with these elastic curves. If you have any questions, you can put it in the comment section. I will try to answer it. The other thing I want to draw your attention to here is this guy. So I will post homework 6 very soon, right? If it's not already posted by the time I post this lecture. But the first problem is going to have you plot the display shape for segments AB and BC, right? So plot from 0 to L. I'm giving you all the parameters. So the P is 10, the L is 240 inches, the E is 29,000 KSI, the I is 250 inches to the 4th. So you should be able to plot this in Excel, and you should be able to show that at L over 2, at L equals 120 inches, that the displacement and slope for segment AB is exactly the same as the displacement and slope for segment BC. Right? Okay, hopefully this one actually posts with sound. Sorry about all the confusion and difficulties with this.